Polymers from Natural Building Blocks by Sam Lobato.
Question: what links starch and polyvinyl chloride, goats, and flak jackets? What makes rhinos so damn horny? The answer, of course, is polymers. But what is a polymer? Well, we shall see.
A polymer is a simple concept to grasp. It is a large molecule made up of many individual, smaller, repeating molecules. Let's take polyvinyl chloride for an example. This is a molecule of vinyl chloride, aka chloroethene. It consists of 2 carbon atoms, 3 hydrogen atoms, and a chlorine atom, joined in the middle by a double bond. Polyvinyl chloride is simply many molecules of vinyl chloride joined together, as you can clearly see here. Although a real molecule of polyvinyl chloride is much, much larger, it can contain up to 1,500 molecules of vinyl chloride, and is used for such things such as piping, for example water pipes. That is the basic idea of what a polymer is.
Now that you have a basic idea of what a polymer is, let's look at some examples of polymers from natural building blocks, both those produced naturally and those synthesized. Natural polymers are incredibly common, yet are rarely thought about as typical polymers. Examples of these include all proteins, for example, as they are made up of individual repeating units of amino acids. For example, keratin, a substance of nails, hair, and some animal forms as a protein, yet people rarely think of their own hair as a polymer. Further examples of polymers include DNA and RNA, made up of individual nucleotide monomers. This, for example, is cytosine, one of the molecules in human DNA. Starch and cellulose, a typical component of, say, a potato, are both polymers, composed of individual glucose monomers. The difference is, starch is composed of amylose and amylopectin. Amylopectin is branched, meaning the chains cannot pack together as tightly as they can in cellulose, because cellulose is composed of individual straight chains. These chains can get very close together, aided by the hydrogen bonding, meaning they produce a much stiffer, much more stable molecule in comparison to starch. Rubber is used for a lot of things, such as boots, or gloves, or car tires, and is a good example of a natural polymer that literally grows on trees, Hevea brasiliensis to be precise. Natural rubber is found in the form of polyisoprene. Shown here is an individual isoprene molecule. However, synthetic rubbers also exist, such as synthetic polyisoprene amongst others, and is a good example of man trying to synthesize a natural polymer to make it more commercially viable, more of which we'll find later in this video. Natural polymers have the very rare property of having a polydispersity, which is a measure of how different the lengths of each polymer is of one or very close to it. What this means is, each length of polymer for a particular molecule will be the exact same, provided it's produced naturally, which is impressive to me. If you consider that every molecule of DNA in every single cell of your body has precisely and utterly the same length down to the atom, of course, provided mutation hasn't taken place. So that just about wraps up natural polymers from natural building blocks. There are others, such as chitin or amber, but we can be moving on to either natural polymers that have been modified, or synthetic polymers that are made up of natural building blocks. Now I'm going to talk about some polymers from modified natural building blocks. This is when the polymers have natural monomers, but these monomers are then chemically altered in some way, either pre- or post-polymerization. The primary example of this is nitrocellulose. Our story begins with one Mr. Charles Friedrich Schoenbein, who, while working with highly imitable chemical practice, managed to spill concentrated nitric acid everywhere. He reached for his cotton apron to wipe it up, and upon drying up, however, the apron promptly exploded. Thus, the nitrocellulose polymer was born. Using its ultra-superpowers, nitrocellulose dedicated its life to exploding, mostly, in the form of smokeless powder, which was a significant improvement over black powder, namely being smokeless, as the name implies. Nitrocellulose was also used for celluloid tapes. Unfortunately, it still retained its tendency of burning to cinders when it was least expected to, leading to it being phased out over time, because, even when it didn't burn to cinders, it also tends to degrade rapidly. Celluloid film was replaced with cellulose acetate, another cellulose-modified polymer, this time with the nitrate groups replaced with acetate groups instead. Cellophane and rayon are also polymers originating from cellulose that exist in this half-synthesized, half-natural world. Starch, another natural polymer, can also find itself resident within this zone, in the form of thermoplastic starch. Thermoplastic starch is formed when ordinary starch is treated with heat and water, which breaks apart the intermolecular hydrogen bonds between the starch molecules. Then, plasticizes, chemicals that make a polymer softer and more malleable are added to the starch to form thermoplastic starch as we know it. Thermoplastic starch can have different properties depending on the water content and which plasticizer they use, which leads to a different variety of uses, such as in food packaging.
Synthetic natural polymers, aside from sounding like an oxymoron, are the term given to polymers whose monomers are found or produced in nature and are then polymerized by man. Bioplastics, as they are sometimes called, have several advantages in comparison to conventional synthetic polymers. So now that you know what a biopolymer is, let's have a look at some examples. Polylactic acid is a polymer formed of lactic acid monomers. Lactic acid you may recognize as the substance that builds up in your muscles after strenuous exercise due to anaerobic respiration. Lactic acid is produced commercially by fermentation of feedstock such as cornstarch by bacteria. The resultant lactic acid is then extracted, processed, and finally polymerized to form the polylactic acid we all know and love. Polylactic acid can be used for such things as disposable tableware or tea bags, and due to its biological origins can be broken down in industrial composting facilities to simply carbon dioxide and water. Polyglycolic acid is another biopolymer made up of glycolic acid monomers. Glycolic acid can be found in nature in things such as sugar beet, but can also be produced synthetically or by enzymatic biochemical processes. Polyglycolic acid is useful in the medical world for producing stitches and sutures that will break down in the human body, thus making them useful, for example, in sewing up the insides of people and the outsides, as they will not have to be removed. Bioplastics are usually produced from natural renewable feedstocks, in comparison to conventional synthetic polymers, which are produced from non-renewable hydrocarbons. Obviously, this gives an advantage to bioplastics in terms of sustainability of production. Bioplastics are also usually biodegradable, meaning they can be broken down by certain living organisms, such as bacteria, fungi, or sometimes even humans. This means they will not take up space in landfills, as they will eventually biodegrade over time. In comparison, synthetic polymers will be hanging around for millions of years, taking up space in the environment. All these advantages come at a price, however, as bioplastics are usually more expensive than their conventional synthetic counterparts. This is in part due to the newness of their production, as well as the use of their feedstock in other purposes, such as producing bioethanol, or of course, simply being eaten. The line between synthetic polymer and biopolymer can be blurred at best, as can be seen in renewable polyethylene. This is polyethylene where the ethene monomers have been formed by the fermentation of feedstock to produce ethanol, which is then dehydrated to produce the ethene monomer. Is this a biopolymer or is it a synthetic polymer? There's no definite answer, but here's another example of one that straddles the line between synthetic and biopolymers, or as I like to call it, the curious case of the goat and the flak jacket. Spider silk. It's strong, it's tough, and we just can't get enough. That's why Nexia Biotechnologies came up with a plan. They would take a goat. They would then genetically modify this goat in order to produce spider silk proteins in its milk. The proteins would then be extracted, purified and spun into threads, in order to produce a silk-like protein. After all, it's far easier and more commercially viable to have a herd of goats rather than a herd of spiders. They succeeded, or at least partially, and the resultant polymer was christened biosteel. Biosteel was planned to be used in a lot of things, amongst others, flak jackets, anti-ballistic missile systems, and medicinal purposes. Well, that's it. I hope you've learned something about polymers, both those produced naturally and those produced synthetically, what they're used for and how they are made, and had a little fun while doing so. If you have anything to say about this, any questions or any comments, you can send me an email. Thank you for listening, ladies and gentlemen, and goodbye.